Proteins are the active molecules of life. They underpin virtually every functional process inside our bodies. I'm Tuomas Knowles. This is our microfluidics laboratory at the University of Cambridge, Department of Chemistry. Proteins are linear polymer chains, like this belt. In order to be functional, however, they have to fold into specific three-dimensional shapes. Sometimes, however, proteins can misfold into shapes, which make them prone to stick to other proteins that they are not supposed to interact with. This type of misbehavior commonly results in disease, the most striking example of which is Alzheimer's disease, the most common form of dementia. To address this challenge, in our laboratory, we developed fundamentally new ways of probing protein interactions in real time, under native conditions, on the scale of a living cell.
So in order to be able to study what the misfolded proteins are doing, we need to be able to separate them from the folded proteins. And we've managed to find a way to solve this problem. So we've done this by developing a microfluidic device, and this device is able to separate different types of proteins. These allow us to apply an electric field through this chip, and this electric field is what separates the proteins according to if they're misfolded or if they're correctly folded. And we see that the unhealthy misfolded proteins, these separate out further than the healthy, well-behaved proteins.
It turns out that the behavior of fluids changes dramatically when we confine them to a scale which is similar to that of a living cell. In particular, flows go from being turbulent, which is our everyday life experience of fluid behavior, to being laminar. In order to illustrate laminar flow, we will use a highly viscous fluid, glycerol. If I now turn the handle the other way, something very interesting happens. What we find is that the fluids completely unmix again. Even though this behavior is unusual for macroscopic fluids, this is what happens to typical fluids when confined to the size of a living cell, or the sizes that we use in our microfluidic devices, and this allows us to do experiments which are simply not possible under bulk conditions. One of the things that we have discovered here over the past couple of years that we are very excited about is an increased understanding of the mechanisms by which molecular chaperones can curtail protein aggregation. This clearly shows that it is possible to suppress this aberrant process by chemical means, and this gives us tremendous optimism for the future.
Hello, my name is Sven Royal, and as a member of Corpus Christi College, Cambridge, I studied natural sciences way back in 1976. Tuomas Knowles and his work in the Sir Rodney Sweetnam laboratory to discover the role of misfolding proteins in causing disease is just one example of how research in Cambridge is addressing huge societal problems such as Alzheimer's and Parkinson's diseases. I know from personal family experience how devastating these diseases can be in robbing people of their dignity and independence. Both the teaching and research in the chemistry department were inspiring over 40 years ago, and they continue to be so today. I'm very grateful to Cambridge for the opportunity it gave me, and I feel lucky and privileged to have the opportunity now to give something back to help others. Reflecting on the benefits I received, I funded a 3-year postgraduate scholarship to create an opportunity for an outstanding young student to experience the same life-changing education that I enjoyed. Our outstanding universities have for generations kept the UK at the forefront of global scientific research. But we shouldn't take these institutions for granted. And that's why I'm committed to support chemistry at Cambridge, and I very much hope you will too.